Hi, this is Mr. Erlin, continuing with our unit on circles in Geometry Spring 2020. Completing these notes, we're going to get some definitions to get our understanding of circles a little bit deeper. This is section 10.2 within our book. We begin with a central angle, which is an angle formed with the center as the vertex. In other words, I start with a circle, and if I take my center and extend out with two radii, I produce what looks like a slice of pizza. This little angle here is called a central angle. What makes it interesting in circles is that there's something called a circular arc. If I take a circle and I chop off a part of it, like for example the crust of that slice of pizza we just looked at, then we're going to call that a circular arc. And when we have these arcs, they have two components, or they can be measured in two ways. They can either be measured in degrees, like how much of the 360 is it, or they can be measured as a measure of length. Like if you were to take a tape measure, how many inches is it, or how many feet is it, or how many miles is it? We'll talk more about that later. Within those arcs, in the event that you're looking at a small arc, an arc that takes up less than 180 degrees, we call that a minor arc. If it's more than 180 degrees, goes more than halfway around, it's called a major arc. And if it's exactly 180 degrees, it's called a semicircle. It's half a circle. When we talk about circles and we want to refer to them, we always name our circles by the center points. So if this is a circle with A as a center and B and C and D all on the circle, we would call this circle A. If I wanted to name this central angle, we would name it the same way we always have. I could call it angle CAB or angle BAC, where the endpoints are the endpoints of the angle meeting the circle. When we talk about a minor arc, remember a minor arc is less than 180 degrees. So if we're talking about this dotted red arc from B to C, we could call that arc BC. And just like we did with segments, remember that if we had segments, we'd put a segment over the top, or if we had a line, we'd put a line over the top. Now, if we want to talk about the segment from B to C, we put a segment, if we want to talk about the arc from B to C, we put an arc over the top. By default, we've all agreed that you want to go the shortest distance. So if I want to talk about this minor arc for B to C, I would use two letters, just B and C, describing it with an arc as the shortest distance. If instead I intend to take you the long distance around, I'm going to use three letters, not only the starting point and the ending point, but the D in between to demonstrate that I'm going that path. So BDC would be the major arc, and B the long way down to C. Just some factual pieces here that get us some foundational knowledge. In a circle, the measure of the minor arc and its corresponding major arc will both add up to 360, because that's how many degrees go around a circle in all. Thus, the measure of BC arc plus the measure of BDC arc equals 360. Measure of a complete circle is 360. Minor arcs are part of the full circle. If the first full circle is 360, and inside here, these central angles also, these two make a straight angle of 180, these two make a straight angle of 180. Therefore, a full circle on the inside is also 360. Therefore, in the event that you have a central angle, its measure of 83 is going to match the arc that it meets. In other words, the measure of a central angle is equal to the measure of the minor arc that it subtends. So 83 and 83 are the same size. If I knew that this was 35, I'd know that this is 35. And of course, I could say if this is 35 and this is 83, I know that's 118. I could find this one by saying 180 minus 118, because this is a diameter, which makes this a semicircle, equals 180. And by subtracting that 118, I could discover that 62 is both the measure of this arc and the measure of that central angle. A couple more parts of 10.2. Since a circle, no matter how big it is the same shape, just a larger or smaller version of it, effectively they're all similar. They're dilations of one another. We learned about that 2 units ago. two circles are congruent if and only if their radii are congruent. If they've got the same radius, then they're going to be congruent circles. But if they've got different radii, they're just similar. Within circles, you can only have congruent arcs, either in a single circle or in two congruent circles, if the two minor arcs are congruent. I have two congruent circles, and I know that this one and this one have the same radii, and I know that this is 30 degrees and this is 30 degrees, then these arcs are also going to be congruent arcs. Here's an application that's interesting and leads us somewhere fun. This is a pie chart. So instead of having degrees up here, I've got percentages. This is 20%, this is 30%, this is 50%, adding up to 100 as pie charts normally do. The question is, what's the measure of the minor arc BC? You want to find the degrees that makes up. Well, I'm going to suggest that the way to do this is by using proportions. 20% is out of the full 100. So 20 is to 100, as the degrees measure is to the full degrees in a circle, which is 360. So 20 is to 100 as n is to 360. That's a valid proportion. Therefore, I can cross multiply to solve. 100m equals 7200. Divide by 100. I get n is equal to 72 degrees. That's the measure of this arc. As we mentioned earlier, there's also the opportunity to discuss lengths of arcs. How many inches does it take? How many feet does it take? In other words, even though I might have, say, these three similar circles, and whatever degree measure this is, it's the same as this central angle. Therefore, that's the same measure as this other one, because it's also the same as its central angle. These two arcs, then, both have the same degree, the same measure, but they're clearly not the same size. This one's longer. You had to walk this distance versus walk this distance. They're different. That comes back to the idea of the circumference of a circle that you learned about some years ago. We can say that the formula of the circumference of a circle is c equals 2 pi r. Pi is 3.141596, blah, blah, blah. It's a rational number. We use this symbol to indicate it, and we'll actually solve a lot of our problems using that symbol without resorting to a calculator for a rough estimate of 3.14. R stands for radius. People often get confused with pi r squared, which is the formula for the area of the circle. We use that later, but not quite yet. To find the length of an arc, not its degrees, but now we're talking about its length, its portion of the circumference. We can use the same proportions we used up here. The length of an arc is to the circumference, the length all the way around, as the measure of the arc is to the degrees all the way around. So the length is to the circumference as the measure is to 360. So in this problem, to find the length, for example, we'd say the length is to 12 pi, because that's circumference equals 2 times pi times 6, which is 12 pi. And that's what we plug in there. Length is to 12 pi as the measure, 60 degrees, is to 360. And then cross multiply. So 360L equals 12 pi times 60. 360L equals 720 pi. Just leaving the pi symbol there. Divide by 360 so that I'm left with just L. And on this side I get 2 pi. That's a precise answer. It's the perfect answer. It's not rounded in any way. In this case, it asks us to round it to the nearest 100th. So I also plugged in 3.14 for pi, and I get 6.28 as my approximated answer. If that helps, that's chapter 10.2 from our circles unit.